Okay, so this is lecture 22, and in this lecture we're going to be talking about some of the crazier stuff we've come to realize about the nature of our universe on the largest scales, stuff that we've learned over the last sort of 80 years or so. In particular, the last really 25 years, things have gotten really crazy in the sense that we now have a model of the universe that's in pretty solid footing, where what's shown here is a pie chart of what we think the universe is made of. Now, the thing that's kind of bizarre about this chart is that only 5% of the universe is actually in the form of something that's you would call normal matter. So that's anything that's on the periodic table of elements, okay? Anything made of protons and neutrons. So anything we're familiar with in our everyday lives is in this single 5% pi wedge. Everything else is totally sort of foreign to us in terms of its makeup. So 25% of the universe is in the form of something called dark matter, and I'll explain about what that is a little later in this course. But basically, dark matter is something that's it's got mass, but it's weird in the sense that it doesn't interact with light. So it's invisible and it doesn't shine. So if you shine a flashlight on it, the light will go right through it. The other thing that's very weird about dark matter is it doesn't interact strongly with any normal matter. Okay? So what this means is it has really weird properties. So for example, if you have a ball of normal stuff, and if you took that ball and you threw it at the wall, it bounces off the wall. And why does it bounce off the wall? What force is it that makes the ball bounce off the wall? Does anyone know? Is it gravity? Who thinks it's gravity? Is it the strong nuclear force? Is it the electromagnetic force? Good. Okay, someone explain to me why it's the electromagnetic force. What's happening with the electromagnetic force? It makes the ball bounce. Yeah.
The electrons in the wall and on the ball tell each other.
Great. So the electrons in the ball feel the electrons in the wall, and since they have like charge, they repel. So the electrons in the ball repel the electrons in the wall, and they bounce off each other. Okay, that's why balls bounce off walls. That's why we don't fall through the floor. Okay, that's why things are solid. If instead you had a ball of dark matter traveling towards the wall, it would go right through the wall. Because dark matter doesn't interact strongly with the electromagnetic force. Remember, the electromagnetic force is light. And dark matter, that's why it's called dark, doesn't interact with light, doesn't interact with the electromagnetic spectrum, it doesn't have a charge, and so it would go right through the wall. So dark matter behaves in a way that's very weird. However, if we had a ball of dark matter and threw it at the wall, it would fall. Because it's attracted to the Earth's gravity, we think dark matter does feel gravity. Dark energy is even weirder than that. Okay? Dark energy is a different thing than dark matter. Dark energy is almost like an anti-gravity. It's not quite accurate to say that, but it acts in a very strange way. And that'll be the first part of the lecture. I'll talk a bit about dark energy and why we think it's there. But dark energy is some strange stuff. So as we understand it now, imagine you had a box. Okay, you put some stuff in the box, and you weighed the box. Now, without opening the box, let's say I put some marbles in the box, okay? I put marbles in the box, close the box, I weigh the box, it weighs a pound. Then my box is stretchy, so I just take my box and I stretch it out. I don't open it, I don't put any more marbles in it. I weigh the box again. What's it going to weigh? Same weight. It's not going to change because there's still the same number of marbles in the box. Now let me get a box, open my box, I'll go to the store, buy some dark energy, put the dark energy in the box. Close the box. Now I stretch the box and I weigh it. So whereas before I stretched it, I weigh the box, it weighs a pound. I stretch the box, I weigh it, now it weighs 2 pounds. Dark energy is weird in that basically what you can think of it as, it's almost like an energy density of empty space. And so the more empty space you have, the more mass and energy you have. And that matters a lot on the scale of the universe because the universe is expanding, and as the universe expands, it basically contains more and more energy density. And that makes some weird stuff happen in the evolution of the universe. So these two crazy pieces of our cosmic puzzle are bizarre. Something I like to tell our chancellor whenever I get a chance to talk to him is, while every single department on this campus, other than physics, is focused on this sliver of the pie, it's only physics and astronomy that studies the whole pie. So I don't understand why funding is not allocated in the same way. So if you remember in 1929, this was when Edwin Hubble published his famous diagram that demonstrated that the universe was expanding, that the farther you go, farther a galaxy is from us, the faster it's expanding away from us. So this was Hubble's diagram. And one of the crazy implications of Hubble's observation here, his discovery, is that this means that you could play a game of tracking things backwards in time. This appears to suggest that the universe is expanding, and so if the universe is expanding, you can try to extrapolate it back to beginning time, right? And so you can start to ask a very fundamental question. If this is today, how long ago was everything at a single point? And you could think of that as the beginning. So you could start asking really fundamental questions like, how old is the universe itself? Last time we spent quite a bit of time talking about how to do this, and in fact your rocket mix module you'll take this weekend is also about this. But basically it turns out that if you measure the slope of that relationship between velocity and distance, that's called Hubble's constant, and if you invert it, it has units of time. And that Hubble time is a really good estimate, or sort of a limit, on how old you think the universe can be. So if the universe has always been expanding at its current rate, that is, galaxies have always been flying apart from each other at the observed rate they're flying apart from each other, you can back that back out and figure out when they were all at a single point. So something's been traveling at a constant rate, right, away from us, and it's a given distance from us. It's very easy to take that velocity and that distance and figure out at what time it was at 0. And so the time that they were at 0 is sort of this estimate for the age of the universe. So this is called the Hubble time. It's 1/h². And in fact, it's a limit in the sense that if galaxies have only been slowing down because of gravity, that is, if they've been expanding away from each other and only slowing down, if you assume that they haven't been slowing down, then this provides kind of an upper limit on the age of the universe. And I gave this analogy of a ball. You take a ball, you throw it up off a planet. If the planet's very light, you can plot the distance from the planet's surface as a function of time, and it'll just be a constant rate. That is, the distance traveled at any given amount of time is always the same. It travels at constant velocity up because there's no force of gravity acting on the ball if the planet's light enough. But if the planet gets heavier and heavier, you would throw the ball off at a fast speed, which is like a steep slope, and then it starts to slow down, and so the rate at which it will travel away from the planet's surface goes slower and slower and slower the heavier the planet is. And actually, you know, if the planet's heavy enough, it can even go to a point and then come back down. If you are up on a ladder, which you can think of as today, right, and you measure the ball go up from you at some speed, you can ask how long ago did it leave the ground? Okay, so this is again an analogy of galaxies launched off from a single point, and you want to ask when they were all together again. If there's no gravity operating on those galaxies, there's no gravity tugging on the ball, it's very easy to figure out when it first left the ground. And that, on this plot, that would correspond to this distance between now and when it left. Notice that if the planet's heavy and the thing's been slowing down, then the time when it left the ground is shorter than this naive estimate. So this would be like the analogy to the Hubble time, whereas this is the analogy to this shorter time if the planet's been dragging on it. Okay, are there questions about this? Okay. Now, the universe is the same deal, right? The universe has mass in it. The universe tugs on everything else because of gravity. So if there's lots of stuff in the universe, you have all this stuff that's initially launched from a single point. The more mass there is in the universe, the more those galaxies are going to be slowing down over time. So in the limit of a completely empty universe, you'd have a trajectory of separation between galaxies versus time that's basically a straight line. And here we are today measuring this slope. That's the slope of Hubble's line. Whereas in the past, things were moving, if the universe has a lot of mass in it, you could imagine a situation where in the past things were faster, now they're slower and they're going to get even slower. Or you could even imagine if there's enough mass in the universe that at some point the universe is going to stop expanding and recollapse again into a big crunch as opposed to a big bang. Now, so it depends on how much mass the universe has, and there's a critical density where you'll turn around and fall back again. Now, so this is the age of the universe for the Hubble time, and this is an example for the age of the universe if you have a certain higher density of stuff. But the point is that this Hubble time is longer than the age of the universe. So this is a good limit on how old we think the universe could be. And by the way, if we go out and measure all the mass and count up all the mass we think the universe has, and that includes in dark matter and normal matter, then the total amount of mass is somewhere between what would be in this purple line and what would be in this cyan line. But the point is it's naively less than this cyan line. That is, the age would be smaller than what you would estimate from the Hubble time. Now, the value of h naught is critical, right? And we talked about this last time. The bigger value of h naught, the faster the universe is expanding, and that means the more recently all the galaxies were together, right? The faster they're moving, the faster they'll get to the point they are now. So the bigger h naught is, the shorter the time they've been traveling apart. So the way to see this graphically is now, what if you took h naught and made it bigger? It would just take all these things and make them steeper. So h naught is the slope of this relation, so if you make a steeper slope, all the lines do that, right? So with bigger h naught, this time is shorter than it was before. Okay? That's a regular h naught, there's a bigger h naught, all the times get shorter, the bigger the slope is. Does that make sense? We can go the other way around, and things get longer. Okay? So another one of these cases where it took me like 4 hours to do this. I'm going to show it to you 5 times. Okay? Wow, look at that. Yeah. So, okay, so that's the point. Okay, so this means that measuring the slope of this line, right? I mean, like one of the most boring things you could do, at least I remember like talking about measuring slopes of lines when I was in high school in math class, being like, why am I measuring slopes of lines? That's just horrible. But measuring the slope of this line is exciting. Because if you can measure the slope of this line, you're learning something about the age of the universe just by measuring the slope of a line. Okay? So there was this huge quest, this giant investment of resources and activity of astronomers for a long time to figure out what the slope of this line is. Right? And if you recall, Edwin Hubble got the slope wrong. He measured his own constant wrong, okay, by about a factor of 10. And so that was one thing that people had to sort out. Now, it turns out that what you want to do, right, is you want to measure the velocities of galaxies away from us. You can do that. It turns out that's pretty easy. That's just the redshift measurement of its light. The distance is hard, okay? You've got this Cepheid variable relationship, but it's hard to find Cepheid variables in galaxies that are really far away. And so there's lots of things that you have to look at to try to figure out what the distances to galaxies are. It's always the hard thing in astronomy. How far away is that thing in the sky? So it's the galaxy distance things that are really hard, but we're finally getting to a point now where we're actually able to measure the value of this h naught to good precision. And within about the last 25 years or so, we sort of settled on what the actual value of this was. It turns out actually that one of the prime reasons why the Hubble Space Telescope was built was to measure this number. It was one of the key projects that people wanted to have Hubble for, was to measure the slope of this line, because the slope of this line is, again, a key to the actual age of the universe itself. And the consensus value for this value of h naught now is somewhere around 70 kilometers per second per megaparsec. And let me remind you again, this is a weird unit, right? Kilometers per second per megaparsecs. Let me just pause on it for a second. The reason why it's kilometers per second per megaparsec is we're plotting kilometers per second on the y-axis and megaparsecs on the y-axis. So when you do a slope, kilometers per second on the y-axis and megaparsecs on the x-axis. So when you do a slope, which is dy dx, you have to do the units of the y-axis divided by the units of the x-axis. So it's velocity per distance. Okay? Now, you can still look at this and say, but this is still a ridiculous unit because I've got a unit of distance divided by a unit of distance. And so really they should just cancel out, and this should have units of 1 over time. And in fact it does. Because if you take 1 over h naught, you get a time. Okay? So it all actually makes sense. It's just sort of a weird choice of units. Are there any questions about that? Your rocket mix module is going to go through this. So it'll step you through this if you're a little confused by it. Okay. Now, remember how when I first talked about Hubble's measure of the Hubble constant, there was this age crisis. And the age crisis was that when Hubble initially measured an H naught of about 500 or 600 kilometers per second per megaparsec, and the implied Hubble time then was less than 2 billion years. This was a big problem because we knew that there were rocks on Earth that were much older than that. So there was clearly a crisis, something was wrong. It turned out that the distances Hubble used were wrong, and the value of H naught he should have gotten should have been a lot lower than the one he got. And when you corrected for that, the universe got old again. However, a new age crisis appeared. And this one was even harder to understand because now we thought we had our distances under control. Specifically, if you take this consensus value of H naught and you invert it, you find that the Hubble time is about 13.9 billion years. This is definitely a long time. It's definitely older than the Earth. The problem is we've now been able to measure ages for stars, for individual stars and star clusters around our galaxy that age date those stars at somewhat over 13 billion years. So we know that there are stars that are almost as old as this reported upper limit on the age of the universe. If you then throw in the matter that we know is there, that shrinks the age of the universe even more compared to the Hubble time, and it makes the universe younger than the stars we see. So this was a crisis. And proof of this is the cover of Discover magazine of 1995, that famous magazine Discover. And the crisis in the cosmos, this is stuff that popped science articles, we don't understand what we're doing, there's this big crisis going on. So then, what are we going to do after this, right? So then everyone else just read that article. Astronomers discovered something that was completely crazy. What they discovered was that the universe is not slowing down. Okay? Remember in my analogy about a planet and a ball? Take a ball, you throw it up off the planet. The most extreme thing you can think of is there's no mass on the planet at all, so the ball doesn't slow down on its way up. However, what's happening now is we're actually seeing that if you look back at how fast galaxies are expanding away from themselves at early time, you see that the universe is actually speeding up in its expansion. It would be just as weird as throwing a ball up in the air and having it not slow down on its way up, but to sort of go up a certain distance and then take off like a rocket up. So now, for example, in that case, if you had a ball come by you up on your ladder, and rather than it slowing down on its way up, it's actually speeding up. That would mean that your estimate for the age was totally screwed up. That it could have actually taken longer to get to you than the naive expectation of going at constant speed. So that's what we saw. So astronomers were looking at galaxies that were so far away that we were effectively looking at their expansion rate back in the past. And what was discovered is that back in the past, the universe was slowing down a little bit, but then is now speeding up. So there's a cosmic acceleration that appears to be going on. And this cosmic acceleration is that, sometimes people call it an anti-gravity effect. So it's sort of defying gravity by accelerating up in its expansion. And like I said, it's just as weird as throwing a ball up, and rather having it slow down, it just speeds up of its own. It just takes off the Earth. Okay. So this actually reconciled the age crisis. So rather than having something like this purple line, you had something like this green line, and now suddenly the universe is old again. And now everything is starting to make sense. Except that this doesn't make any sense at all. How the heck is the universe accelerating its expansion? Who ordered that? That's just so weird. Okay. So this solves the age problem, but it introduces something of a new problem. So I'll get to that in a second. Now, how did astronomers actually do this? This was a huge feat. A couple of different teams of astronomers, one on the West Coast and one on the East Coast of the United States, ended up doing this, and they would eventually win the Nobel Prize for this observation. What they were using is they had a new standard candle. If you remember, Henrietta Leavitt had discovered sort of the first important standard candle in astronomy, the Cepheid variable stars. And what she discovered is the rate of the variability of the star correlated with how intrinsically bright it was. So all you had to do was measure the rate of variability of the blinking of the star. You knew how intrinsically bright it was. You could treat it as a standard candle and figure out how far away it was. The problem is these were just individual stars. And at some point, when they're farther than 100 megaparsecs away, you just can't see them anymore. It turns out that nature has given us another standard candle. And these standard candles are called supernovae, specifically a type of supernovae called type 1a supernovae. And it turns out that there's a relationship with them. Also, in the rate at which they get bright and dim off again, if you can measure that rate at which they get bright and get dim, you can infer what their intrinsic luminosity is and use these supernovae standard candles. And the awesome thing about supernovae, why supernovae are great standard candles, is they're crazy bright. So you can see them really, really far away. Okay? And so there are these plans that people, or these investigations that people started where they were just searching for supernovae blowing up in the sky. And they discovered a bunch of supernovae, they figured out how far away they were, and they were able to create these Hubble diagrams that went way out to billions of light years. And it was with those observations that they figured out the universe is accelerating. Okay. Are there any questions about this? Okay. Now, what is this acceleration? Well, it turns out that one of the best explanations for what's causing this acceleration is Einstein's old cosmological constant. If you can remember, the thing that I said was called his greatest blunder was the fact that he didn't buy that his own equations should allow the universe to expand. And so he introduced, kind of out of nowhere, this new constant that he stuck into his own equations to kind of keep the universe from collapsing on itself or expanding. And this was called the cosmological constant. Right? So while Lemaitre was saying, look, hey Einstein, your equations let the universe expand. Isn't this awesome? We should explore an expanding universe. Einstein's initial reaction to that was, that's ridiculous. That's the ugliest thing I've ever heard of. Maybe my equations are wrong. I'm going to change my equations and add a new cosmological constant to keep the universe static. What's amazing is, now today, the actual best fit to explain the data of the acceleration is a cosmological constant. The cosmological constant just comes in on the other side of the equation, and it allows the universe to accelerate in its expansion. So we call this phenomenon of acceleration dark energy. Okay? Now, that just because we have a name for it doesn't mean we understand it. It's sort of the parallel dark matter, but it's even weirder than dark matter. It's something that's making the universe accelerate, and we don't know what that something is. There's a few different ideas for what it might be, and like I mentioned, the leading idea right now is that there's something called the cosmological constant. So this cosmological constant, one way to think about it is the energy of empty space, that the vacuum of space itself actually has an energy density. And it turns out that if the vacuum of space has an energy density, according to Einstein's equations, this will drive the universe to accelerate in its expansion. Right, so this is sort of Einstein's I told you so. So his greatest blunder in the end might end up being like his most incredible triumph because he predicted this insane thing that no one was expecting. There's another possibility that what we're seeing that's driving this accelerated expansion is something that's come to be known as quintessence, and you could think of that as sort of evoking a new force of nature. So rather than there being four forces of nature, there might be a fifth force, this quintessence, that is perhaps driving the universe to accelerate, acting like a vacuum energy and making this happen. A final possibility is that the reason why we're inferring this weird energy density of empty space is that in fact general relativity is wrong, in that while Einstein's equations do better than Newton's equations and at certain scales and at certain speeds and at certain energies, it may be that ultimately even Einstein's general relativity is wrong, and that needs to be modified on the largest scales in order for us to understand why the universe is accelerating. But amazingly right now, this is actually an incredibly good fit to all the data we have. That it's a cosmological constant, Einstein's old blunder could be the truth. Are there any questions about this? I know this is sort of like blurry and kind of fast, but are there any sort of questions that spring to mind about this? Okay. So this is what I've talked about so far. Now there's all the normal stuff we know about. And again, most of that turns out is hydrogen and helium. Okay? You are a teeny tiny sliver of this. Everything heavier than hydrogen and helium is just a tiniest little sliver. Okay? So that's why you are so special. Okay? You are special in the universe. But even the normal matter is special in the sense that dark energy makes up something like 70% of the energy density of the universe. Now, this other chunk here is the dark matter, and that's what I want to talk about in the last half of lecture. The story of dark matter is a long one, actually, and there have been hints that it's there for a long time. But the first hints of it were occurring actually in the 1930s, almost at exactly the same time that Hubble was solidifying the existence of the expanding universe. There were some anomalies that were being observed that suggested that something funny was going on in the motions of galaxies. So I will come to this later. So in the 1930s, or the early 1930s, people were beginning to recognize that if you look at galaxies all out in space, and you go out and you measure their velocities, they're generally moving away from us. Okay? And so this kind of picture emerged that it looked like everything's expanding away from us. And Hubble could produce diagrams that sort of look like this, where you've got the velocity of recession and the distance, and then you have a distribution here. I think I showed this plot before, but let me ask this again. Does anything look kind of funny in this plot? Does something stick out to you in the diagram that looks kind of weird? Yeah, you're motioning. What is it? Yeah, this thing here is what you're talking about. Do people see this? Okay. What's going on here? Right, let's think a little bit about what this means. This means there's a bunch of stuff that's all at about the same distance. And while on average all that stuff is moving away from us, just like everything else would be along that Hubble line, some of the stuff is actually moving away from us more slowly, and some of the stuff is moving away from us more quickly. One way to think about that is, well, what this is it's a ball of galaxies that are all traveling together in the cosmic expansion, but they're orbiting around themselves in a cluster. So the ones that are sort of coming towards you, okay, it's all being pulled away from you like this, but while it's coming away from you, it's sort of doing this orbit. So the ones that are coming towards us a little bit are receding less fast, and those are here. And those that are orbiting out, away like this, are the ones that are poked up here. And so you see structure within that velocity diagram. Okay? So what we're seeing there is sort of bound clusters of galaxies that are themselves broke off from the cosmic expansion, and it's sort of like a little bubble of space-time that's being carted away, but within that bubble the stuff's orbiting around itself, like a hive of bees. Does that make sense? Okay. For example, here's the Coma cluster. So this cluster of galaxies, you can image it from the ground here, and it's beautiful. It's got all these galaxies all clustered together in the same spot. They're roughly all moving at the same speed, but they're orbiting around each other a little bit. So it turns out that by measuring the velocities of galaxies with respect to each other in these clusters, you can measure how massive the cluster is. All right? And the basic way you do that is, if you have small velocities, okay, that means there's not much mass there to keep these things orbiting around. But if you have big velocities, there's a lot of mass, right? So for example, the Earth is going around the sun at a few tens of kilometers a second. That's because the sun has a given mass. If the sun was a lot more massive, in order for the Earth to be there and not have crashed into the sun, it would have to be going faster. Right? So if you measure the orbits of planets around stars, you can figure out how massive the star is. In just the same way, if you've got a group of galaxies orbiting around each other, you can measure the mass of that group of galaxies. Does that make sense? Okay. So in 1933, there was a fellow by the name of Fritz Zwicky who was not studying how fast the universe expands. He was trying to figure out how much mass there was in this cluster of galaxies, the Coma cluster. And what he said was that they're moving too fast. He measured how fast they're moving with respect to each other, and he found that they were moving way too fast compared to the amount of mass he could see. So he could add up all the mass in stars, right? He could see the stars, he could see the galaxies. He added up all the mass they had, He calculated how much velocity they should have, and he found out that they're moving way too fast, right? So either these galaxies are about to fly apart from each other and never come back again. So what we're witnessing is sort of a weird flyby event, which would be very odd. It would just sort of be a strange setup. Or these things are actually bound to each other in orbits, and there's a bunch of mass that we can't see. And Zwicky would call this dark matter. He said, look, there's some dark matter there. There's some matter, some mass that we cannot see that must exist around this cluster, and I don't know what to make of it. Now, Zwicky was an interesting character, as you could tell from this picture. That's sort of a picture is worth more than 1,000 words, right? I mean, look at this guy. People thought he was strange. He was cantankerous. A lot of people didn't like him. This symbol right here was he was calling people. One thing that he was known for was calling people spherical bastards. Okay, and this is sort of a physicist joke, but a sphere is an object that is the same no matter from what direction you look at it. Okay, so a spherical bastard is a bastard from no matter what direction you look at the person, right? So this was something that he would do. So that gives you a sense of the kind of person he was. And a lot of people didn't like Zwicky. They thought he was a little bit nuts. And so people sort of said, well, you know, that's crazy Zwicky, whatever he's doing with the dark matter and the clusters, whatever. Okay? And it turns out another astronomer looked at another nearby cluster that he could study, and he saw the same thing. But again, it was sort of put in the dustbin. People were just trying to figure out that the universe was expanding at this time. Didn't make much of it. But today, we can go and look at this same cluster. Here it is in visible light. We can now have X-ray telescopes. And if we look at X-ray telescopes around this cluster, we see that there's a huge mass of hot gas. There's not that much mass in the hot gas to make up for the extra missing mass, but the temperature of this gas is huge, okay? The gas is so hot that it could not stay there unless there was a giant amount of mass to hold it there. Okay, it's got a tremendous amount of pressure. And again, this is direct evidence today that there's some additional mass in there confining all of this hot gas. Notice that the hot gas is all here centered around this, but there's no clumps and stuff. It's as if there's some giant, you know, ball of something holding all this stuff together. Okay. So people didn't really believe what Zwicky was doing or didn't pay that much attention to it, but the idea of dark matter gained sort of more relevance in the 1960s. And specifically, there were researchers like Vera Rubin, who's a pioneer for this kind of thing. What Vera was doing was she was not interested in measuring how fast the galaxies were moving away from us or towards us in bulk. At this point, the techniques and the instruments have gotten sophisticated enough that now she could actually measure how fast the galaxy was spinning as a function of radius from its center. So she was measuring how fast it was spinning around. Now what she expected to see was that when she looked in the middle of the galaxy, she expected the stars to be whizzing around fast. But as you go away from the middle of the galaxy, as the light falls off, the gravity from that middle stuff falls off, and you expect the speeds of the stars to be going slower and slower and slower as you move away from the edge of the galaxy, right? In the solar system, it's like this. Pluto is going around very slowly compared to the Earth because it's very far away from where the sun's gravity is. But what she observed was something very different. What she observed was that as she went out at the galaxy, things kept spinning just as fast. This was very weird, okay? Because this should not happen if the mass traced what we saw going on with the light. And she saw this again and again. As we look at more and more galaxies, we see this continuously. Every big spiral galaxy we look at, if we go out far enough in its rotation curve, we see that there's missing mass there. And again, this is consistent with the idea that there are these big extended blobs of mass out there, something we call dark matter, that are beyond these galaxies. So again, in the 1960s and the 1970s, people began to actually take seriously this sort of crazy idea that there was all of this extra mass out there that we couldn't see. But the real sort of linchpin for this, the thing that really solidified in most people's minds about why we really do now believe that this extra mass must exist, has to do with the actual structure of the universe itself on the largest scales. And the basic argument goes like this. We can actually go out today with telescopes and look at what the universe was like a few billion years ago, okay, and even farther ago. And we can make maps of what the structure of the universe was like at those times. Okay, so and that's sort of what this is. This is we're here, and this is a galaxy count map starting today, going back in time this way. Now, one thing I think you could probably see right away is that here around us, which means today, right, because we're looking back in time as we go to things that are farther away, stuff is all clumped up. The universe is clumpy, very clumpy, a lot of structure. But as you go back in time, it's smoothing out. There's less and less structure. And in fact, with other things not shown in this plot, we can go way back to something like 300,000 years after the Big Bang and measure the clumpiness of the universe in, just in sort of diffuse gas at that time. And the universe was almost perfectly smooth in the very beginning. Somehow, the universe went from a state that was almost perfectly smooth, with no structure at all, to today we look around us and it's a vast network of complicated galaxies. Now, how you go from a little bit of structure to a lot of structure is basically gravity. Okay? If you have two things, if you have a perfectly smooth sea of stuff, just a little bit of extra stuff right here, that little bit of extra stuff is going to attract the other stuff because of gravity, and over time, that region with a little extra stuff is going to get richer and richer and richer, and the empty regions are going to get emptier and emptier and emptier, right? So the rich are getting richer and the poor are getting poorer in this sort of gravity model, okay? It turns out, however, that if the only mass you have is the normal stuff, you don't get enough structure growth. You can't go from the universe that's this smooth to a universe that's this clumpy in this amount of time. So people have tried very hard to make that happen, and you can't make it happen. If instead you put this dark matter in, and you calculate what happens, you get amazing results that look sort of just like this. I'm going to show you an example of this now, I think. Okay. This is a numerical simulation that actually seeds a universe that starts off very, very smooth, just like we observe it to start. And now we've added all of this dark matter to the mix, and we've let the clock start running. So when this gets to 0, that's today. So it started about 13 billion years ago, and it's going to get to 0 today. The color code is density. And so what you're seeing here is that as time goes on, this dark matter starts to attract other dark matter. And you start to see structure develop that looks eerily like the real universe. That is, you see these networks of clumps that live along filaments with vast open voids, okay? And you don't get anything that looks like this at all if you don't put the dark matter in. If you only put normal matter in, nothing works. Okay? It doesn't look at all like the real universe. But if you put this stuff in, the same stuff that we see evidence for from galaxies spinning and galaxy motions and clusters, etc., you start to see something that looks a lot like the real universe. So the idea here is that each one of these clumps would host a galaxy inside of it. Let me just show you something that's kind of crazy, amazing really. What's shown here is a map of the real universe. So these are actual galaxies that are observed in the real universe, and it's the same kind of plot that I showed you before. And you see all this filamentary structure, and notice it's getting less clumpy out here at early times. This one in red here is actually a simulated universe that's done in a supercomputer that includes dark matter and dark energy in the amounts that we think are there. And the amazing thing is that it works. And if you, in fact, do statistical comparisons between this side and this side, you find that they are statistically indistinguishable. So even though it might be kind of hard to believe at first blush, there are lots of things that are pointing to this idea that the universe on the largest scales is made of stuff that's entirely foreign to us. And by studying the universe, by going out and counting galaxies and making maps and then trying to make sense of that in the context of the sort of the science that we understand, we've come to this sort of crazy conclusion that the universe is actually made of stuff in broad brush that's just completely different than us. That is, there's a sort of entire dark universe out there, right? That could have all kinds of complexity going on that doesn't interact with us. But we're somehow able to sense it because we understand the laws of physics so well for gravity and this stuff that we do understand, that we're starting to get a glimpse of some deeper makeup of the universe that we otherwise wouldn't know about. Okay? So one of the things that's going to happen in a week from today is you're going to get a test. And when you have a test, what that means is someone on the other side of the test has to come up with questions. Now, things like this are sort of, you can't resist coming up with a question like this, right? So I've just given you 4 reasons why we think dark matter exists. So you can pretty much bet that there's going to be a question on the exam that revolves around what are the 4 reasons that dark matter exists, okay? So let me just summarize it for you here, in case you're interested in that, next Friday. So what are the reasons why we think dark matter exists? 1, the first thing I talked about with Zwicky, galaxies living in galaxy clusters are moving around each other really fast, much faster than they would be if there wasn't extra mass holding them together. The other thing we know is that if you actually look at galaxy clusters now in the X-ray, you can see evidence that there's gas in these clusters that's crazy hot, at crazy high pressure, and there's no way this gas could be confined to that high pressure if there wasn't some force holding it there. Because if there was no force holding it there, it would just pop out because it's such high pressure, it's so hot. So if you infer how much mass has to be there, that's again consistent with all of the mass that we think has to be there just from the speeds of the galaxies themselves. The next thing I talked about were galaxy rotation curves. Remember the picture of Vera Rubin there trying to map out how fast galaxies are spinning as from distances from their centers. What she discovered was that galaxies are spinning very fast in their outer parts, much faster than they should be if the only mass that was there was the light. Okay? And so instead of galaxy rotation curves falling off, they're flat. So the speeds with which galaxies spin on their axis, again, is indicating that there's more mass there. And finally, something that you shouldn't forget, a really important piece of evidence that the dark matter is there, is the large-scale structure of the universe itself. That it's very, very difficult for us to understand how galaxies could possibly be distributed in the broad brush way they are throughout the universe without allowing for this additional mass. It turns out, by the way, that there's actually lots of other reasons why we think this stuff has to be there. There are lots of different sort of pieces of evidence where we're studying all the time, and it keeps coming back to this crazy notion that there's a lot of mass out there that we don't know what it is. Okay. So are there questions about this? Okay. So what is this dark matter, right? Well, the funny thing about dark matter is we've got a name for it. We know how much there is, but we don't know what it is. We know what it's not. Okay? It's not like anything normal that you're used to dealing with. So it's dark, and the reason why it's called dark matter is that it does not shine. Okay? It doesn't emit light, it doesn't glow, and it's see-through. It doesn't actually interact with electromagnetic force much at all. So like I said, if you had a ball of dark matter and you threw it at the wall, it would go right through the wall. One time I was giving a public talk to a bunch of kids, like young kids, like 7, 8-year-olds. And I used the same analogy. I said, look, if you had a ball of dark matter, okay, and you threw it at the wall, it would go right through the wall because dark matter doesn't interact with normal matter. This little kid in the front row raised his hand and he said, if dark matter doesn't interact with normal matter, how do you pick it up and throw it? I said, do you want to come to school at UC Irvine? Because that's a good question. But that kid was thinking, that's exactly right. You could not pick it up. So now when I give that analogy, if you go back and watch the video, I don't say pick it up the first time I introduced this. I just said if you had a ball and it was going that way. So I avoid that from the little Einsteins in the audience. Now it's matter because it attracts other matter via gravity, right? It pulls on itself, it pulls on itself, it pulls on other stuff via gravity. It has mass. So it's something. We think it's made of particles or something. So that these particles are different than the particles that make up you and me. Now you might think that sounds crazy, right? You might think, look, it's crazy that there exists some kind of particle that would go right through the wall. But there's all kinds of particles going through the walls right now, okay? All of you on your laptops on Facebook right now rely on that, right? There's radio waves going through the walls all the time. Those are photons going through the walls, right? They're carrying your text messages, they're carrying your Facebook posts or whatever you're doing, right? Okay? There's other particles called neutrinos that we now know exist. They're extremely weakly interacting, okay? The person who discovered the neutrino was Fred Reines. Okay, that's why this is called Linus Hall over here. He won a Nobel Prize in 1995 for finding the first neutrino. Okay, so we talk about him a lot at UC Irvine. He was one of our founding faculty. But those neutrinos exist. They go right through walls. Okay, so it's not entirely crazy that there is some other kind of particle that exists out there that interacts very, very weakly with us, that tugs on other kind of particles with gravity, and in fact shapes the large-scale structure of the universe. Now exactly what these particles are, we don't know. There are lots of ideas for what they should be, lots of weird names and stuff they have. I won't get into all that. But it's fair to say that most cosmologists, although not all, but most cosmologists think that what the dark matter is it's some form of subatomic particle that was born in the Big Bang with all the other subatomic particles, and that has this residual effect of having mass and interacting very weakly with neutrons and protons and electrons. Are there questions about this? Okay. Who buys this? Who thinks this seems reasonable? Who thinks this is complete nonsense? Come on, I know it. I know there's people who think it's complete nonsense. Okay. That's okay. Really? That many people buys this? They think this is reasonable? Good. Okay, that means I've done all right. Okay. So this is where we are today, right? This is where we are. We have these huge uncertainties in our understanding of what the universe is. We've put ourselves in this weird box. We think we've sort of glimpsed a sort of bizarre thing about the universe, that it's composed of stuff that's entirely different than the stuff that makes up you and me that are easy for us to do experiments with. But this is amazing, right? Now, if you want to think about what dark matter does, okay, rather than what it is, what does it do? We know that. You could think of dark matter as sort of being the engine of galaxy formation. It's the thing that allows stuff to clump together and eventually form stars and make stuff. Without the dark matter, there would be almost no structure in the universe as far as we understand things today. So that is, if you remove this stuff from the pie, we are not here. So somehow it seems to be vital in making stuff. This piece is sort of the opposite. It's driving the universe to expand at an ever-accelerating rate. So far, far in the future, actually, this stuff is going to dominate. The universe is going to be expanding so fast that no new galaxies are going to be able to form, no new stars are going to be able to form, and it's going to basically shut down creation. So right now, we're living at this kind of nice time where we've had enough time to form and evolve, but we haven't had enough time for the dark energy to sort of take it all away. All right. I'll just close with this. I mean, this is sort of an amazing thing we've come to know about the universe, and we're still trying to puzzle it together. If you think back to when I showed the first slide on the very first day, I talked about how our ancestors looked up at the night sky and believed that it was a window into something deep about the universe that they didn't understand. If you look at this pie chart, you can understand that they were right. We're still trying to figure this stuff out. But by peering up at the cosmos, we've come to understand things that are far beyond anything I think we could have guessed, or even the most eloquent poets or imaginative poets could have guessed about what the universe is like. All right, we'll see you Monday.